Alright, we're starting chapter 3, and this lecture is the first of two on chemistry and the environment. This is chemistry and environment lecture number 1. Well, you can probably guess at least some of the reasons why we talk about chemistry and environmental science. It's, of course, a general understanding of chemistry is crucial for understanding almost every environmental issue, such as how gases contribute to global climate change, how pollutants cause acid rain, the effects of chemicals on the health of wildlife and people, water pollution, wastewater treatment, hazardous waste, atmospheric ozone depletion, and all the energy issues. In this first lecture, we're going to discuss the following and introduce the following concepts. We'll talk about atoms and elements. So we'll start out with a discussion of matter and then talk about what matter is made of. We'll talk briefly about isotopes and ions, discuss molecules and compounds, and last, pH, acids, and bases. So let's start with the concept of matter. Okay, all the physical material in the universe, anything that has mass and occupies space, is made up of matter. Okay, so that's what matter is. The matter itself, then, if we break it down into its parts, is made up of atoms and molecules and compounds, which we'll talk about in a little while here. So essentially, the smallest part of matter is atoms. There is an important idea concerning matter, a scientific law called the law of conservation of matter. And essentially, the idea is of the law of conservation of matter is that matter is conserved. So it can be transformed, so a substance can be changed from, say, a solid to a liquid, or it can be recombined with something, but it cannot be destroyed or created. So we have the matter that's there. It doesn't go away. It does get recycled, right, in nutrient cycles and ecosystems, and it changes forms. Atoms and elements. In nature, there are 92 elements, and essentially an element is a fundamental type of matter that cannot be broken down into substances with other properties under normal circumstances. Chemists recognize 92 naturally occurring elements, elements that occur in nature, and there are 20 artificially created ones, so ones that can only be created in the lab under very specific conditions. Each of the elements has characteristics, and those characteristics are derived from their atomic structure, the number of protons, neutrons, and electrons that the element has. The elements, chemists have then abbreviated each element with a chemical symbol and organized them into a periodic table of the elements, which summarizes the information about the elements and some of their reactions with each other and their stability, etc. Let's take a look at some of those abbreviations. Here's some of the elements that I would like you to know in the beginning of the course here. We may add on to this list as we go on. Okay, so you can see here, hydrogen, the element hydrogen is abbreviated with the letter H. Sulfur, over here, abbreviated with the letter S. Carbon, letter C. Chlorine, Cl. Oxygen, letter O. Potassium, letter K. nitrogen with an N, phosphorus with a P, and calcium with a Ca. So here are 1, 2, 3, 4, 5, 6, 7, 8, 9 elements for you to learn the chemical symbol for, and we may add to that list as we go on. Let's talk about atoms and elements a little further. As we said, an element is a fundamental type of chemical substance, and they're composed of atoms. Each atom has a specific number of protons, and protons have a positive charge. Electrons have a negative charge, and neutrons, which are neutral and have no charge. Okay, so they lack an electrical charge. Each element is given an atomic number. Okay, it's not listed here. The atoms, which is the atom's number of protons. Okay, so those positively charged protons is the element's atomic number. Okay, so let's look at some examples. First, here's carbon, letter C. Atomic number is 6. That means that there are 6 protons, and if you look up at this figure above, atomic structure, you can see that the protons are the red particles, and there are 6 of those. Carbon has 6 neutrons. The neutrons are shown by these gray balls here, right? And you can note that both the protons and the neutrons are in what are called the nucleus or center of the atomic structure. Okay, little difference than a cell nucleus, but still an area where these particles are centered. The electrons are located outside of that area, and they have the negative charge. You can see they have the little negative sign, and there are 6 electrons out here, and that is a balanced design. So you've got 6 protons positive charged and 6 electrons negative charged in carbon. Nitrogen, abbreviated with the letter N, atomic number 7. It's got 7 protons in the nucleus, 7 electrons in the nucleus, and 7 neutrons in the nucleus, and 7, 1, 2, 3, 4, 5, 6, 7 electrons out there. Last, let's take a look at phosphorus. Phosphorus has an atomic number of 15, so that must mean there's 15 protons. There's 15 neutrons in the nucleus, and there are 15 electrons floating around the outside, those negatively charged particles. Let's talk for a second about isotopes and ions. Okay. Start with isotopes. Atoms of a given element with differing numbers of neutrons are referred to as isotopes. Okay? Differing numbers of neutrons. Because they differ in mass or weight, right? Isotopes of an element differ in their behavior. Some may be radioactive and go through a decay process, right? They decay until they become non-radioactive or stable. And we can use that information that we know about the radioactive decay to date certain circumstances. Okay, so as you can probably think about here, because these organisms, isotopes have different masses, right? Neutrons must have some weight to them. Okay, so they have a mass. Electrons really don't. They're so small they don't. But protons and neutrons both have a mass associated with them, and different numbers of protons and or neutrons will give the element a different mass. Now, ions are electrically charged atoms or combinations of atoms resulting from the loss or gain of electrons. Okay, so ions have a charge, either a plus or a negative associated with them. because they have lost or gained electrons. If they have more electrons, right, they're going to have more electrical or more negative charge, they're going to have a negative sign. If they've lost electrons, right, they're going to have a positive sign because they have more protons than electrons. Okay. So here we go. Isotopes, right, different masses, different numbers, same number of protons, same number of neutrons, I'm sorry, electrons, but different numbers of neutrons, and ions, different numbers of electrons. Here's some examples. Okay, here's the hydrogen atom. Hydrogen has one proton, one electron here. If we add a neutron, right, you get a hydrogen isotope. One proton, one neutron, one electron, and it's written like this, an H with this superscript 2 before, okay, indicating that's a heavier isotope of hydrogen. Here we go. Here's hydrogen that has lost an electron, okay, so the electron is gone. Now it has more positive charge than negative charge, and we put a plus sign. So there's one proton, no neutrons here, and no electrons. This would be H plus, or hydrogen ion. This is an example of an isotope, right? Isotopes are the ones that have half-lives, have different masses. This is an example here of an ion. Ions are charged because they've lost or gained electrons. Atoms bond to form compounds and molecules. So they come together and they combine. And molecules are combinations of two or more atoms. Okay. So for instance, they're going to have, this means that the atoms are the same. So for instance, an example here is oxygen gas. Its molecular formula is O2, O with a little subscript 2 behind it. And that indicates that there are two oxygens there combined together, right? Two atoms of oxygen. And that gives you a molecule of oxygen. Compounds are molecules consisting of multiple elements. Atoms, are held together by these different bonds, right? So here are a couple examples of compounds. Down below here, covalent bond. We won't distinguish right now between covalent and ionic bonds, but there are two different main types of bonds here. Carbon dioxide, right? CO2. So two molecules or two atoms of oxygen, one atom of carbon combined together with chemical by bonds. This is an example of a compound. NaCl, right? One atom of sodium and one atom of chlorine. Right, we didn't talk about sodium yet. This is also an example of a compound. Two different atoms combined together. Here's some other examples of molecules and compounds. Technically, hydrogen and oxygen and nitrogen and chlorine are all molecules, right? Because you can see that the atoms are the same. These are all important atmospheric molecules or compounds. And I end up myself discussing them all as compounds, where we should be more careful, I suppose. Down below, nitrogen oxide, NO is the chemical formula there. Water, which you're familiar with, two atoms of hydrogen, so shown with this 2 here, one atom of oxygen, that gives you water. Nitrogen dioxide, one atom of nitrogen, two atoms of oxygen as shown here. And carbon dioxide, a carbon molecule with two or carbon atom with two atoms of oxygen tied on or bonded on. The last topic I want to introduce here is the concept of acidity and pH and basic. The pH scale, which I'll show you in a second, ranges from 0 to 14 and quantifies the acidity and basicity of solutions. A solution that has a concentration, a high hydrogen ion concentration, which is greater than the hydroxide, right? This is new OH negative ion concentration, then the solution is acidic. So the more the difference is, the greater the difference, the higher the concentration of hydrogen ion compared to OH, the more acidic that compound is. If the hydroxide ion concentration is greater than the hydrogen ion concentration, then the solution is basic. So again, it'll become a stronger base the more, the greater the difference is between hydroxide and hydrogen here. Here's the way we typically look at this. The pH scale measures acidity and basicity. We use pure water as the neutral or pH 7, sort of the middle part, right? It's a neutral solution. Anything with an acidity greater than, acids are less than 7, so lower than 7, and bases are greater than 7. Okay, as far as they're on the pH scale. So here we go. Here is neutral. We got pure water. Anything less than 7 going this way, from normal rainwater, which is about 5.5, acid rain a little under 4, the acid in your stomach around pH 3, lemon juice, extreme acid rain, and car battery acid down here, below 1. These are very strong acids down at the bottom, okay? All below 7. But as you go down, the acids become stronger, okay? If we start at neutral again and go up, right, we've got seawater, which is a little more basic, right? It's how little pH is 8. And as we go this way, we see soft soap of a pH about 9, ammonia somewhere in there in pH 11.5 or so, and all the way up to sodium hydroxide solution up at the top of pH 14. So very strong bases up here, intermediate bases, not very strong bases below, and neutral, okay, on this pH scale.